Hello everyone, welcome back. In the last few classes, we have looked at the governing equations, which are basically spatio-temporal partial differential equations. We looked at dimensionalization of those equations. We looked at the character of different terms of those equations, basically which terms represent the hyperbolic portion, which term represent the elliptic character, and so on and so forth. Okay. Now, it is time to basically start discretizing those equations, so that we can solve them on the computer. As we have discussed in the first class, that CFD is basically solving these partial differential equations on a computer using in a discrete form, because the computers do not understand the continuous function or the calculus, but they do understand the algebra or arithmetic in more precise, and they can do operations like the arithmetic operations like summation, division, multiplication, and so on and so forth. So, despite of the fact that the differential equation that we have are basically the continuous equations, we will try to discretize them on a given grid. Okay, we will have different number of grid points to approximate different derivatives and try to solve them on a computer. Okay. So, let us start with the discretization. So, if you look at the Navier-Stokes form in the matrix form that we had discussed. So, we had like du by dt plus df by dx plus dg by dy, okay, plus dg dh by dz equal to 0, right. So, where this is in 3D, that is why we have written in dx dy dz, okay. And f had got two parts, all f, g and h, which was first part was inviscid and second part was viscous, okay. And then for the inviscid part, for example, if you write, you will have rho, rho u, rho v, rho w and rho e, this is your u, okay. And similarly, you can write f as rho u square plus p, okay. And then probably there will be rho u v and rho u w term, and similarly you will have rho u v, okay, rho u w, okay, and rho h u, okay, rho e u, or you can write in enthalpy form also rho h u, right. Similarly, you will, if you go to the g term, that will be here rho v and then your rho u v. So, if you write this is the inviscid term, there will be viscous term as well. You can write the g term also, which is basically rho v, rho u v, rho v square plus p plus rho v w and rho h v, right. And similarly, we will have the w term. So, if you look at this form closely, you have two ways, I mean two things that you need to discretize. These derivatives that you see del by del x, del by del y and del by del g, they represent the spatial discretization, okay, the spatial derivatives, and then you have del by del t, right, which is the temporal discretization or the temporal derivative, right. So, discretizations approximate the derivative, right. So, before going to this very complex form of the inviscid term and viscous term and the temporal and spatial discretization in all three dimensions, let us look at a very simple form, which essentially captures the main message of these equations, which is a simple equation del u by del t plus del f by del x equal to 0, right. So, if you want to solve this on a computer, this problem del u by del t plus del f by x equal to 0, you have to basically, because you cannot calculate del u by del t without discretizing on a computer, right. Unless it is a function like, for example, u equal to sin omega t or something like that, then you can have the inbuilt functions in the computer, where you can say del by del t will be sin omega t, that will become omega cos omega t and so on and so forth, right. But in most of the cases, these functions are not well defined functions, right, not in the sense that they are not basically the mathematical functions derived in the literature, right. They can be very complex functions, okay. So, what you do, you will discretize. So, what you are doing, that this is my, let us say this is I plus 1, this is I minus 1, sorry, I plus 2, I minus 1, I minus 2 and so on and so forth, right. So, this we have discretized in the space, right. And similarly, let us see if I have this time, okay, let us say this is my time. So, this is we will start from let us say n equal to 1 and then we go to n equal to 2, n equal to 3 and so on and so forth, right. So, we are going to solve these equations. So, initial condition will be given. So, n equal to 1 is let us say this is your initial condition, which you have to start with some suitable condition, and similarly at I equal to 1 and I equal to n, let us say this is I equal to n, you will have the boundary conditions. These parts are the boundary conditions. So, these are called the boundary points, and all these points basically I equal to 2 to all the way to I equal to n minus 1, these are called the interior points. Which needs to be solved using a suitable discretization scheme, right. So, from your elementary classes you might be knowing that you can use any kind of scheme to solve these equations. Let us say if you want to approximate this del f by del x, right, at point I, okay, we are calculating at point I. So, what you can do, this is basically the very crude approximation, this is delta f by delta x, okay, at I, okay, and where delta x is very small, okay, and then only you can approximate this. And delta f I could be written f I plus 1 minus f I by delta x I, right. So, this is how you can approximate del f by del x at I. Similarly, you can go to I minus 1, I minus 2 all the way to I equal to 2 and all the way to I equal to n minus 1 also, right. Similarly, if you look at the temporal term, okay, so if you use the temporal term, that is del u by del t, okay, let us say you want to find out at n plus n, right. So, this will be I will use superscript for the time. So, this is will be n plus 1 minus n by delta t, where delta t is your the time step in your time discretization. So, just like in the space you have discretized, say let us say your length is 1, okay, from 1 to n and you took 100 points, right. So, if length is 1 and you took 100 points, let us take 100 on 1 points to be more precise, okay. So, I mean to make it as a good number. So, this will be 1 by n minus 1 is your delta x, right. So, 1 by 101 minus 1, that will become 0.01, right. So, this is the size between 2 points delta x I, if it is a uniform grid. Okay, you may not have the uniform grid, that means your points are not equal distance, and then you have to basically keep track of the delta x at every point, right. And similarly, you can have the, let us say you want to go from time t equal to 0 to t equal to let us say 1 second, 0 second to 1 second. Now, you cannot go directly from 0 to 1 second, and there are basically if you try to jump from 0 to 1 second, for example, from initial condition to the final condition directly, you will see that your solution will blow up or your solution will be very inaccurate. Okay. There are criterion that depends on that basically decides what should be your time step based on your the size of your grid and your convection speed, okay, or even the diffusion. Okay. So, if you use both those things, this equation can be approximated like this. Okay. So, this is your continuous form, this is your continuous form and this is your discretized form, right. And of course, when you are going in time, so you have to basically have the initial condition at n equal to 1. So, that is why you have written at every I, right. So, this is u I n plus 1 and u I n. So, the subscript denote the spatial discretization and superscript denote the temporal discretization, right. And if you write del f by del x equal to f I plus 1 minus f I by delta x I, it will look like this. You can take it on the right side, okay. And finally, you will get an expression which is u I n plus 1 equal to u I n minus del t by del x I f I plus 1 n minus f I n, right. So, and at nth level, if you start from some initial condition, you know these values, okay. You have fixed the delta t, you have fixed the delta x I, Okay, you know the value of u I at n, and you can calculate the next point of u I n plus 1. Next time you go from n plus 1 to n plus 2, then n plus 2 to n plus 3, n plus 3 to n plus 4, and so forth, and that is how you keep on marching till you go to the final time step, right. And if you have a uniform grid, you will have this delta x I will become just the delta x, because the distance between 2 points are same everywhere in the uniform grid. Okay. This we have discussed earlier. So, this is how you can solve using a very simple minded approach, where what we have done for del f by del x, we have taken the forward differencing, that means we have taken the I plus 1 point and I point, and for I also, for time also we have taken the forward differencing. Okay. Of course, you cannot take backward differencing in time. If you take, then you need to know the solution which is before your time, right. So, you are starting from n equal to 0, and you need to have solution which is available at n minus 1 if you do the backward stepping in time, right. Of course, there are the central differencing approach in time also, which are basically a leapfrogging kind of schemes, which we will discuss later. So, you can use that, provided you have some other scheme to start the solution, right. You can start from forward differencing in time, and later you can switch to let us say the backward differencing or the central differencing, because you know the solution at the previous to previous time step also, right. But as a simple minded approach, you can write it like this, right. Now, this is how you are discretizing using the forward difference, but there are many ways to discretize this derivative, and the solution of your CFD depends on how well you can basically approximate this derivative del f by del x. Okay. If you can approximate it very well, okay, very close to what you would have got by taking by using your calculus, then your solution will be very accurate. In the spectral method, which we have discussed, that they approximate this derivative exactly, okay, provided you have a periodic boundaries, and that is why the spectral methods are most accurate. But in the finite difference approach, or in finite volume, or even in finite element, right, you have a limited precision or limited accuracy of this discretization, but you need to make sure that that discretization is good enough to basically give you a correct solution, and that is where the grid independence comes into picture. We will discuss about those grid independence later, but right now we want to approximate del f by del x as best as possible. In the finite volume, basically we try to solve an integral form of this, which is the weak formulation, and we use a Green-Gauss theorem to basically get the flux at the boundaries, okay, and that is a slightly different approach. In the finite element, you have the basis function, and to get the derivative you write the function in terms of the basis functions, and then you get the derivatives from that. In the finite difference, what we do, we make use of the Taylor series. Okay. So, you write the f at I in terms of Taylor series, okay, I plus 1 or I minus 1, and try to get the value of del f by del x at I, del 2 f by del x square at I, del q f by del x q at equal to I, right. And we assume that these functions are infinitely differentiable, right. So, even the truncation error, which is basically the error that when you discretize this continuous function into a discrete form, will be basically available. So, let us look at some of the formulas for the discretization. Okay. So, what we are going to do, so let us make your stencil. Okay, this is your I plus 1, I minus 1, I plus 2, I minus 2, and so on and so forth. Okay. And we want to use the del f by del x at I, right. Your purpose is you want to get del f by del x at I at this point of time. Later you also might want to get this del 2 f by del x square at I, right. Why do you need that? Recall the viscous term, right. In the viscous term you have this the second differentiation, or the section is also available, right. So, first of all let us look at this del f by del x at I. Okay. So, what we can do, so you have I plus 1 and I, let us take these 2 points. Okay. So, you can write f I plus 1, right, which is nothing but f x plus delta x, right. So, if this is my x, if this is my delta x, right. So, you can write it like that, and if you use the Taylor series around x, so that will become f x plus delta x by del f by del x plus delta x square by factorial 2 del 2 f by del x square, of course, everything at I. Okay. Plus delta x cube by factorial 3 del q f by del x cube I, and so on and so forth, right. In the short notation, you can write it as f I, okay, plus delta x f prime I plus delta x square factorial 2 f double prime I, okay, and so on and so forth, right. Now, what do you want to get? You want to get del f by del x equal to I. Okay. So, you can use this equation. So, you can take this on the left side, del f by del x at I would become f x plus delta x minus f x by delta x. Okay. I am taking this entire term on the left side and dividing by delta x, right. Okay. So, okay, this may be on the right side and I am taking other terms on the left side, okay, and minus delta x by factorial 2 del 2 f by del x square and minus delta x square by factorial 3, okay, del q f by del x, right. So, if you ignore these terms, okay, let us say that I am saying that these terms are very, very small, right. So, you can write your del f by del x I is equal to f I plus 1 minus f I by delta x. Right. So, what we did is basically we at I plus 1 we use the Taylor series to get the value from I, right. So, f I plus 1 will be f I plus delta x of I prime plus delta x by 2 of I double prime and so on and so forth, and we got this, and plus there will be higher other terms, right. So, this is called the one sided formulation, and precisely this is basically your forward difference. Why forward difference? Is because we are using the I plus 1 and I. Okay. Similarly, you can go with the backward difference also. We work here. What you can do is that, okay, I don't want to go to I plus 1, I can go to f I minus 1, right. So, that will become f I minus delta x this time, okay, this will be minus f I prime and plus delta x square f I double prime by factorial 2 plus delta x cube by factorial 3 f I triple prime and so on and so forth, right. So, this way if you take this on the left side, so this will become f I prime, which is basically del f by del x I will be f I minus f I minus 1 by delta x, and then there will be plus delta x by 2 f I double prime and plus delta x square factorial 3 f I triple prime, right. So, now you can see that you have made use of I minus 1 and I, right. So, this formulation is called the backward differentiation. This is also one sided formula, but now this is backward. Okay. So, you may be thinking that both are very similar or both are same, but that is not true, because depending on the direction of your convection, one scheme may be stable and another may be unstable. Okay. So, that we will look at the stability of these schemes in the later part of the discussions. Okay. So, we have found the forward difference and the backward difference approach, but in both of these cases you may note that we are ignoring some of the terms. Okay. So, these terms are basically lead to some error, and those are called, there are two kinds of error basically. One is the discretization error, okay. It is also called the truncation error. Discretization is because you are trying to approximate a derivative by using some kind of discrete approach. So, by doing so you are getting some error. So, that is why it is called discretization error. It is also called the truncation error is because you are truncating the Taylor series while trying to get the approximation for your derivative, right. So, that is called the truncation error. So, all these terms that you see here, okay, these are basically the truncation errors. Okay. So, whatever terms you have discarded while trying to approximate your derivative are the truncation errors, right. The one thing that is very important in this truncation error is that you want to basically look at the leading truncation error. So, what is leading truncation error here? In this particular case, the leading truncation error is this one, okay. And why not the terms which are not leading, which are basically the second term, third term, fourth term, and so on and so forth, so many terms. The reason for that is basically the leading truncation error is the biggest error that you have, right. For example, if you see this is your delta x and delta x is a very small quantity, right. The second term that you have is delta x square, right. So, if let us say we had delta x equal to 0.01 that time we took. So, delta x square will be 0.0001, right, 10 power minus 4, right. So, if the delta x itself is small, the other terms will be very small, right. So, what matters most is the leading truncation error. So, this is your leading truncation error, okay, LTE. You have so many truncation error terms, but the leading truncation error is what we will be discussing most, and this is what also gives you the order of accuracy, right. So, what is the order of accuracy? So, whatever the power that you have on the coefficient of your leading truncation error, basically on delta x is your the order of accuracy. So, what it says that with what order your error is going down. So, let us say it were delta x square, right. So, then it will become that it is going down as delta x square, your error is going down as delta x square. So, higher the order of this term delta x, the power of the delta x, the more accurate your scheme will be, because as we will see very shortly that if your grids for a given grid size, you get basically the accuracy very high if you have the second order or third order or so forth. So, this is a first order scheme because delta x to the power is 1. If the delta x, the leading truncation error had the term which has the power of 2, then that becomes the second order accurate. Okay. Now, let us go to the other error, which is the basically the round off error, right. So, round off error is also something which is unavoidable, just like the truncation error. The truncation error is unavoidable in a CFD calculation, and the reason for that is you always have to approximate your continuous function with a discrete function. Okay. So, the round off error is because you have the limited precision of the of your number, right. So, you might be using the single precision. So, single precision you will have 4 bytes, okay, and it may basically you get the accuracy of 8 digits after the decimal point, right. So, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So, this is the accuracy for your single precision. Okay. Similarly, if you use double precision, okay, then you will get up to the approximately up to the 16 digit 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So, this is your double precision. So, this takes around 4 bytes, okay, and this is your 8 bytes, right. So, after the decimal point how many numbers you can preserve, right. So, suppose let us say that your system is very sensitive, that even at the 17th place something is happening, if there is a difference in the 17th place, then some phenomena is changing. So, that cannot be captured by your computer, because that is the limitation of the precision of your computer, right. So, that is what is the round off error, right. So, what we want to do in a CFD simulation is that we once you do the truncation, once you discretize our grid, okay, and try to calculate our values, the approximate function, we want to do some kind of grid independent solution, right. So, what is a grid independent solution is that let us say you are interested in certain variable, right, and you basically refine the grid. So, when you refine the grid, let us say you had delta x equal to 0.01 when you use the 100 points, okay, in a 101 points in a distance of 1, okay, 0 to 1, right. Now, let us say you use 1000 points, right, 1001 points, okay, to be precise, then your delta x is 0.001, right. So, this of course, this is more accurate. Why? Because your truncation error, let us say if you are using a one sided formulation, it goes by delta x, right. Your truncation error or the order of accuracy, okay, goes as delta x, right. So, if the delta x is small, of course, your error is small, right. So, what we want to do is that we want to go to the limit ideally where the truncation error is basically smaller than the round off error, right. So, let us say if you are using a double precision formulation, right. So, you have basically up to 16 digit. So, you refine the grid so much ideally that even if you refine further, you will not see any change. That means, your truncation error is smaller than the round off error. You are approximating the functions as best as you can, right. So, that is an ideal situation. Normally, what you do is that let us say depending on what variable you want to calculate, your temperature, your pressure, your velocity, or maybe there is some gradient quantity like your flux, your heat flux or your skin friction, you want to say see whether the values are changing or not. So, when if it is not changing, that means you say that it is independent of the grid. That means, the discretization scheme that you have used and the grid that you have used is sufficient to give you the solution that is not changing. Okay. The one more thing important that I want to emphasize here is that the non-dimensional helps here also. Why? Because let us say if you take in a dimensional form, so your velocity, let us say you are taking at Mach 0.1, right. So, velocity around 30 meter per second, right, but your pressure is around let us say 101325, okay, Pascal, okay, and then your order of let us say the temperature will be around 300 Kelvin and so on and so forth, right. So, when you basically use a non-dimensionalization form, what you do is basically you non-dimensionalize all the term p u by u infinity, p is p by rho infinity square and t by t infinity. So, they becomes order of around 1. Okay. So, here for example, let us say you are looking at the grid independence of pressure here. So, what is the decimal point that you want to go, right. Let us say you want to take the accuracy of 10132.5.0005, okay, let us say 5 digit, then also it is too much, right, because your number I mean the significant digits are basically very big. On the other hand, let us say if you are going from 30 to let us say 30.2 also 30.1 also, it may change the solution, right. So, your significant digits are different when you are using a dimensional form. When you use a non-dimensional form, because everything is more or less in of the order of 1, it gives you a better handle to basically control your round of error, and you see when your grid independence is coming. Okay. So, these are the two errors which are very important. So, this is the backward differencing formula we have already seen. Okay. And the last thing before we go is want to see the central differencing, where we are going to use the grid on either side. Okay. So, let us say this is your grid I plus 1 and I minus 1, right. So, you can write it here f I plus 1 is equal to f I plus delta x f I prime plus delta x square by factorial 2 f I double prime, so on and so forth. F I minus 1 will be f I minus delta x f I prime plus delta x square factorial 2 f I double prime, and so on and so forth. So, this is 1 and this is 2, right. If you do 1 minus 2, then you can write f I plus 1 minus f I minus 1 will be 2 f I, this term will cancel out. Okay. Okay. No, this term will remain because doing 1 minus 2. Okay. So, that will become 2 delta x, this would cancel out. Okay. The 2 delta x f I prime, okay, and this would again cancel out, and then the third order term will remain. Okay. The something, let me write the third order term also, plus delta x cube by factorial 3 f I triple prime minus delta x cube by factorial 3 f I triple prime, right. That will become 2 by factorial 3. So, that will be 1 by 3, this will become delta x cube by 3 f I triple prime, right, and then there will be other terms. So, So, you can write f I prime would be f I plus 1 minus f I minus 1 by delta x minus delta x square by 3 f I triple prime and so on and so forth, right. So, if you approximate it using I plus 1 and I minus 1, this is what your formulation will be for del A by del x at I. This is del A by del x at I, right. And this is called the central differencing scheme. Why? Because we are trying to calculate the derivative at the center point using the stencil or the points on the either side. So, this is also called the 3 point stencil. Okay. So, number of points you are using in the stencil to calculate the derivative is also very important, because that gives you the order of accuracy. The earlier when we were calculating doing this one sided thing, okay, there were 2 point stencil, right. If you go here, so this is the 2 point stencil. Okay, either you use forward or backward, this is also 2 point stencil, right. So, this is the central differencing. Now, one very important thing you see here, that by just increasing 1 point, what we have got is that our order of accuracy is now 2. Why? Because the delta x has the power of 2, right. So, this is the second order accurate. And how does it matter? If you just want to see, I want to give you an example. Okay. So, let us say you have a 1D domain with 101 grid points that we already took. Okay. This is 0 to 1, 101 grid points. So, your delta x or h, okay, I will use h and delta x interchangeably. So, this distance is h or delta x, right. So, because you have 1 minus 0 by 101 minus 1, right, n minus 1. So, that will be 0.01. So, delta x is 0.01. So, if it is the first order accurate, your order of accuracy goes as delta x, right, which is basically 0.01, that is means error is 1% of the value that you have, right. On the other hand, you do not change the grid, okay, your grid is same, you are using 101 points only, but you are using a second order scheme. So, for the second order delta x square would be 0.01 square, which is basically 0.01%, right. By just increasing one grid point on one side, you see that your accuracy increases drastically. Okay. Now, what error you had around 1%, now error is 0.01%, right. So, you would be tempted to use central differencing everywhere, but let me bring some bad news is that you cannot use central differencing directly in a convection problem. Why? Because accuracy is not everything, your scheme should be stable also, right. If the scheme is not stable, it will blow up, okay, despite being accurate, and there are errors, okay, there are dispersion errors, and that we need to basically see, okay, to determine whether the scheme is stable or not, and there are other approaches also to determine how do you find whether a scheme is stable, right. So, despite I mean getting into the fact that higher order schemes are better, we need to see whether the schemes are stable or not also. So, we will look at some more discretization schemes in the next class. Okay. This is a very preliminary thing, we got the one sided and two sided formulation, but you can have a general approach to approximate the derivative also. So, we will discuss those in the next class. Thank you very much.